Okay, so see if you can take a quick screenshot of that if you're just coming back in. That way you don't have to stress over missing this. Sorry about the noise. Okay, so we're going to look at input, output, and flow. Once we're done with that, those three things, we'll look at 4 equations and just what they are, what their variables mean. We won't work them out today. So I'm going to flip this page. If you missed it, take a quick screenshot. Good. 2, 3. So we're still on the fireplace, and we're going to look at input. And the input's going to be heat energy. Heat is thermal. And it comes from the fire. And it could come from some other heating source, but in this case, it's the fire. Then just as the fire puts heat in the room, we lose it. So heat or something thermal is lost from the room. And that's because we have windows, doors, and just other places for air to flow through, which you need because you can't breathe that fire smoke all the time. So the last thing we look at is the whole system. What's the flow? What's actually happening in our system? So we're going to have thermal energy flows into your system. And it comes in through the fireplace. FP is fireplace. And it flows out of your system through the room. Like a window or a door. We call this this whole flow process, how it goes into from the fireplace and out of through the room, we call it the envelope. And that's just FYI, calling it the envelope. That means, what are we looking at? We put it all together. That's what we got. And the last thing is, we know from our notes that fire, so the fireplace, has low entropy. Entropy can be thought of like energy, like a heat energy that's coming because the molecules are moving crazy in a fire. They're moving fast, they're excited, they're creating heat, they're bumping into each other. So you have disorder and you have low entropy. Entropy is how orderly a system is. So this one has disorder and the molecules are nutso.
Miss J, can you move it down? I can't really see it. Thank you.
You're welcome. Okay, 4 algebraic equations and we're out of here. I'm sorry. Of course, yeah. Prop the door open so you can get back in. I'm never going to hear you with that thing in my ear. Okay, I'm going to flip that page if you guys are okay. I'm going to look at 4 algebraic equations for thermal energy transfer. I have a recording of this and I'll put it online after. I'm going to move this over. All right, first one, Q equals M times C times delta upper T. Q doesn't really mean anything. The dude who discovered the theory just said, hey, look what I found. Let's use Q. This scientist guys are weird like that. So that says Q equals M times C times delta T. Those dots are multiplications. I didn't want to put an X in because it's confusing. You will rarely see an X in an algebraic equation, but you will see it if you study advanced physics. And then it's like, what's happening? Okay, so we got Q. Q is energy transfer. And it has to be in units of joules. So if they give you something else, you have to convert it. And spell joules correctly. Is that still a thing? Do people still use those? M is mass. And this one has to be in kilograms, which kind of sucks because they usually give you your question in grams. I would try not to do that to you, but the end of course exam, it'll give it to you every time. So convert. C is specific heat capacity, and I'm going to give you a definition. Specific heat capacity. This thing is too thick. And that has a really weird unit thing. I won't give you a hard time on it, but you need to figure it out before college. So it's joules, this is the units, divided by kilograms times the degrees Celsius. So that's degree symbol, but that's actually multiplication underneath the division. Not a big deal. It just comes up as you're moving algebraic stuff around. For now, just take a look at it. Don't stress over it. Uppercase T is a change in temp. temperature. The only time I ran into a problem with this is when I had an old school professor that gave us paper quizzes and tests. He was old school. He was super smart. He didn't have time to like do tests. So when he typed this, he would put lowercase t, uppercase t without caring, and you had to know your equation. So if he typed it wrong and you put in time, you should have known better on your equation, and he was not willing to change. I got lucky with my test. I just thought it was temp, and I did it all in temp. But just know that for this equation, that's temperature, no matter what you see like on a paper. The temperature, temperature, temperature. And let's get one definition in here. The other equations are just variables, no definitions. The specific heat. You should learn this in your chemistry class. It should definitely come up. You should do a lot of work on it. If not, you will in college. It's the amount of heat that we need to raise the temp. Needed to raise. Temperature 1 gram of any substance. And you want to make it 1 degree Celsius higher than it was. So it's how much heat required to take a substance, 1 gram of it, and raise whatever temperature it is 1 degree Celsius. So make it hotter. So I take a gram of water, I make it hotter. I take a gram of tinfoil, I make it hotter. Whatever I'm doing, I'm making it hotter by 1 degree. And of course you could do 10 grams and then, 10 degrees, but we just look at it simply like this. As an example, water has high heat capacity. That purple is too thick to write with. So it takes more energy to raise a gram of water 1 degree than for most other substances. So if you put water on the stove, butter on the stove, and you just let them sit there, the butter's going to melt first. Butter has a lot of water on it, so not that quick, but compared to anything else, it takes a little bit longer. So it takes more energy. And you also need a higher heat. It takes more energy to increase the temp of water compared to other things. Okay, 3 more equations. They are simpler than this one. And then you're done. Yeah. Make sure you prop the door so you can get back in. And use the QR code, please. Project lead the way. Okay, so that's your first equation. It's really not that bad because it's just 4 variables total. You use whatever ones you have in a problem, and you solve for whatever one you don't by moving it around algebraically. So that's the tricky part. And we're going to do practice on it tomorrow. Guys ready for number 2? The rest are easier. Okay, so number 2. P equal to Q divided by delta lowercase t. So P should have come up when we were doing electricity, but since we didn't break out the robots, we usually make them lift things and we see how much power they have based on what battery we're using. But since we didn't do that, we didn't see this. You'll get to do it in Ms. Elder's class next year. Both of us are rewriting our curriculum, so it's heavy on hands-on labs next year to make up for this year, because this year's temporary. You won't get to do what we did here, but you'll enjoy her class next year. It'll be good. So P would be power, but we're going to call it the rate of energy transfer. And that's in the unit of watts, because Mr. Watts won the electric race. Watts. So that's how fast the energy gets transferred. And Q is the actual energy transfer, which we know from the first equation. Just don't let the words trip you up. Energy transfer. You see it twice. One is the rate, one is the energy transfer. Now the question we had in number 1 was Q is equal to MC delta T. You can put that in here. You can put MC delta T in here. You can swap out these formulas however makes your question happy. I think that's why I like this stuff, because you can go backwards and forwards, and eventually your mind's like, oh, I get this. So delta T is the tricky part. Because it's lowercase, it's a change in time. I wouldn't rely on someone to put the lowercase in properly. I would memorize that this equation talks about time, and the Q equation from number 1 talks about temperature. Memorize that, not the variables. And the other problem is it has to be in seconds. They love to give you milliseconds. I don't know why nobody talks like that, but because of the reaction, you know, it's how they're filming the reaction. You can lock it up, right? Yeah, you're good. Thank you. So if you get it in the problem in other than seconds, you have to convert. I won't do that to you, but some of the questions will. Okay, it's just 2 more. They're actually the same. They're just moved around. They're the same as each other. They moved around algebraically so you can use them easier. I'm going to move up a little bit. B is equal to K times A times delta uppercase T, all divided by L. You know P is the rate of energy transfer from the one above. I'm just going to point to that because this gets real messy. Your K is thermal conductivity. Some materials don't want to transfer heat for you, and some do. You know, if you're holding something plastic, it's probably not going to get too hot and burn my hand. But if I'm holding something metal, it can get hot and transfer energy. That's what we're going to look at. We'll look at the websites. The P table will give us all that. That's just something you look up. You can solve for it, but no need. And then A, I'm going to go this way, is the area of thermal conductivity. So what space is it being used in? We know the uppercase T is temp. Oh my God, go away from my door. I'm sorry, I'm waiting for him to stop. So the letter L down there is the thickness of the material. We generally see it in meters. Sometimes Project Lead the Way goes into US customaries. So I won't put it there, and I'll tell you specifically what it is when we have a question. But it's usually meters. From college, it was always meters. We have one more, and it's easier than this, and we're done. Oh my God. Go away. He's not going. Okay, one more. You guys okay? Need a minute? There's one more variable. I just want to make sure it's temperature and not time. Yeah. So you already know that K is thermal conductivity, that P is the rate of transfer, energy transfer, L is how thick the material is, A is the area of thermal conductivity, and delta T is a change in temp. Same variables as the last equation, same equation as the last equation. It's just solved for K. Oh my God. It's solved for thermal conductivity because you have to find that sometimes. So it's the same as equation 3, just moved around. Go away. Does anybody need any help with anything? Any questions on getting